Hi, I've got a short, straightforward, but important discussion about how materials respond to forces. First, something called Young's modulus or elastic modulus. This has to do with when you stretch or compress a material. To give us something to think about, suppose I have a metal rod attached to something so that I can apply a force to it. So picture this as, say, a ceiling or a metal plate, and I can apply a force so that I can stretch this wire or rod or whatever it is. The attachment up here is just so if I apply a force down here, I can get an equal and opposite force up here so that this just stretches, it doesn't accelerate. This rod has some cross-sectional area here, A. And what I want to know is if it has some initial length L and I apply a big force to it, how much does it stretch? So it'll get a little longer by some delta L. And I want to be able to compute that stretch. So that stretch won't all come out one end. I'm just showing it that way. So we can just reason through what ought that delta L to depend on. That delta L ought to depend on, well, it ought to depend on how long the rod was to begin with. That is, if it's a really long rod and we stretch it, we get more stretch than if we stretch a little bitty short rod. I think you can see that's reasonable. How much stretch we get depends on how much force we apply. If we apply a great big force, we're getting more stretch than if we apply a little force. That's fairly obvious. And then how much stretch we get ought to depend on how thick the rod is somehow, the diameter, the radius, the area. It turns out it depends inversely on the area. Thicker rods stretch less. So if you got a little bitty rod down to where it's just a little wire, we'd be able to stretch a wire a whole lot more than we'd be able to stretch a thick copper rod or copper rod. And so this depends inversely on the area. As the area gets bigger, the stretch gets less, it extends less. And finally, how much it stretches depends on what the material is made of. If this is made of steel, it stretches less than if it's made of copper. You get a different amount of stress if it's made of brass, different if it's made of wood. I don't want to give the impression it has to be a metal. It's easy to think about a metal. And so there's some constant here that depends on the material. And that's what this stretch all depends on. This constant gets written as something 1 over y. And we'll see why it's written that way in a moment, where this y is something called Young's modulus, or as we saw up above, the elastic modulus. Modulus just means something like constant. So I'm going to rewrite this formula now as putting in the 1 over y. I've got delta L is 1 over y, L over A, F. And the way we usually write this equation traditionally is we write F over A on one side equals, take the y over y, that's why it was written as 1 over y to get this form, times delta L over L. And that's the formula we were actually looking for that relates the stretch to how much force we apply, the size, and the material. So this is the relationship we were shooting for, where this again is Young's modulus. The F over A is called the tensile stress. So this ratio, it's called, so this is tensile stress. Tensile is meaning in tension. So the F over A is tensile stress. The delta L over L is the response That's called the tensile strain. And then again, this Y is Young's modulus, so, or the elastic modulus. So Young's modulus, what is it telling us? This is a material you have to measure or look up in engineering tables. It tells us how much this resists being stretched. So it's a measure of a material's resistance to change in length under an applied tensile stress. So when you try and stretch it, how much does it resist being stretched, depending on what material it is. So Young's modulus, by definition, is a measure of a material's resistance to change in length under an applied tensile stress. You can't just say force for reasons that will come up in a moment, because there are other ways to apply forces that are not tensile stresses. So let's do an example. I'm going to just rewrite the equation here so I can refer to it. So suppose this is just a steel piano wire. So that we're stretching, its diameter is 0.2 centimeters, so 2 millimeters, so you know, about like that. I can't see that in the video. Its length is 1.6 meters to begin with, so that's a nice piano-sized length. And my question is, what is the tension if it stretches 0.3 centimeters when tightened? So we've got the case where, you know, you're inside, got a wire inside a piano, it goes down to some peg, and you turn that peg, and as you turn the peg, this wire stretches, and it stretches by, what did I say? 0.3 centimeters. And we want to know what tension is that wire under. So, what is tension if stretches 0.3 centimeters? So we've got one equation, let's use it. We want to know a force, this F. So F is Y delta L over L, A. Y we have to look up, since it's steel, we look up Y for steel. I've done that. Y for steel is 20 times 10 to the 10th newtons per square meter. If you look these up, sometimes a newton per square meter is a unit we haven't run into yet called a Pascal, PA. That's a unit of pressure actually, but sometimes it's tabulated that way. So if you see Pascal, that's just a newton per square meter. Delta L over R. Notice whatever units delta L are in, if I put L in the same units, they'll cancel. So if this is meters, make that meters. If this is centimeters, make that centimeters. If this is nanometers, make that nanometers. As long as they're the same units, they'll cancel. I need the area. Area is pi r squared. It's really important to find out what area I mean. I mean the cross-sectional area. If you were to slice it, so this is pi. I gave you the diameter, 0.2 centimeters is, so this is, the radius is half that, 0.10 times 10 to the minus 2 meters squared. That area turned out to be 3.14 times 10 to the minus 6 square meters. I hope that's where you can still see it in the video. And I plugged all those in. The 20 times 10 to the 10th newtons per square meter. Delta L over L, delta L, 0.3 centimeters, but I'm going to write it in meters, is 0.3 times 10 to the minus 2 meters. Over L was 1.6 meters. I didn't really leave room for my area, 3.14 times 10 minus 6 square meters. So we've got meters cancels meters, meter squared cancels meter squares. I get newtons, which is what I wanted. That turns out to be 1178 newtons. Real quickly, before I go to the next example for material response, this also works if you're compressing a material. So if I had, for example, like a concrete column at the Parthenon or somewhere, and I applied a giant weight to it to create, some sort of force on top, some sort of great big force. This column would compress a little bit by some delta L, and the same equation works. It doesn't work just for stretching; it also works for compressing. It's that you get then delta L is negative if you take the signs into account, or you could just compute the magnitude of delta L. You could just do it that way. All right. Now, that's what happens if we apply force just along the length. But that's not the only way you can apply forces. There is another way. We can apply what are called shearing forces. And this leads to something called shear stress or shear modulus. Which leads to something called shear deformations. Suppose I start with some block. This will probably be easiest to picture if you think of this as a block of rubber. While we're saying applies to steel or concrete or any material. And now suppose I apply a force up at the top here and a force down at the bottom here. These are called shearing forces when they're offset like this. This is like what happens when you have something like scissors that are just offset from each other just a little bit, like your yard shears when you're cutting branches. So what this is going to do, these forces, I forgot to label it, force, these are going to deform this block. So this block is going to change its shape. So if we apply these forces, the block is going to deform, and you can picture a rubber block doing something like that. If I call this its initial height h, and if it only deforms a little bit, that h height won't change. I'm going to call this little bit delta x is a measure of how much it deforms this distance. Sometimes we can do it in terms of this angle. Is another way deformation is discussed. And how much it deforms its resistance to deformation depends on this area now, this cross-sectional area this way. That's a different cross-sectional area than we had before. That's not very easy for you to see, so I'm going to relabel it. This was the cross-sectional area A. I shouldn't have made so many marks through it. There. Now, if we go through the same sort of logic we did a while ago, what we find is that F over A equals some constant that depends on the material, but it's a different constant. It's called the shear modulus. It's not Young's modulus. Times delta X over H, where this is now called the shear stress, and this is called the shear strain, and S is called the shear modulus. Where this is, S is a measure of a material's resistance to change in shape. So its shape is changing, it's deforming. A measure of a material's resistance to change in shape under an applied shear stress. Measure of a material's resistance to change in shape under an applied shear stress. You might also see this written as a measure of a material's resistance to deformation. Change of shape can be written as, can be called deformation under an applied shear stress. And again, you can look up these numbers. We'll do an example of this with the in class. You'll see it in the homework. I'm not going to do another example in the video. The difference is that you're using a cross-sectional area along the direction of the force, not perpendicular. So if we were doing tensile stress, the area is this way. For shear stress, the area is that way. So you can practice that in your homework, practice it with the in class, we'll do one there, and it's pretty straightforward, but actually very important because it has to do with how materials respond. That material could be, for example, a bone being stressed in some way. So see you soon.